But I do that quite a lot by accident. But anyways, I'm back here. Now I have the chat so I can see people. But yeah, what I was saying on the previous stream was that this Astable Multivibrator goes and it will charge up. Like right now, it's charging up this capacitor. No, it's discharging this capacitor. Wait. Now I'm all messed up. Yeah, it's charging up this capacitor here. And eventually this will hit that 700 millivolts. And it hit it. Turns this on. And then switches, starts discharging this capacitor through here while, I guess, sort of charging this side of it. And then this one is charging this side, which will eventually hit that 700 millivolts, like the last one did. And when it hits that, it will turn on this transistor here, which will again switch the sort of orientation of the charge and discharge of these capacitors. There, now I got it. Chat. Hello. Holy potato. Oh, I am just basically there's this website called Falstad simulator, and it uses JavaScript to simulate different electrical components. And then on their site, I noticed one of my previous streams that there is a lot of inbuilt circuits, example circuits, that I find is very good. And yeah, I'm just looking at them right now and trying to analyze them just with words in a way that makes sense, hopefully. Mostly for my own learning and try to increase my explainability abilities. Yes, thank you. I think it's cool too. The next one is a current source. Oops. I try to make it so that I don't see what the circuit's doing. That time I failed. But anyways, this circuit will be so let's just look at it for a second here. We will have a milliamp flowing through here. So at this point, I believe they usually say about a tenth of that will go through here, or go into this base. So that would be about 0.1 of a milliamp, or tenth of a milliamp. Now, the beta of most transistors is about 100. So, no. No, that's the wrong way to think of it. Sorry. disregard what I said. What I was thinking there was incorrect. So at this point, we're gonna have 2 volts. Now that means we're gonna have about 1 diode drop between the base. Well, the 2 volts here doesn't mean we'll have that. It's just transistors will have 1 diode drop between the base and the emitter, approximately. So say about 0.7 volts. So that means we have 2 volts here. 2 volts minus 0.7 volts. That is 1.3 volts. 1.3 volts. And we got a 1K resistor. Well, that means there will be about 1.3 milliamps going through here. That means that there will be about 1.3 milliamps coming this way. Now there it says 1.4 milliamps, so I would have to assume that means they are taking a diode drop to be 0.6 volts, which some people do. It varies on the diode. Well, I guess here it varies on the transistor. Yeah, so it's not. That doesn't. That tenth of a volt doesn't matter too much for what we're talking about. So let's run this. Yeah, so we got that 1.4 milliamps. Now, what they have this switch here for is to just demonstrate that, okay, we have this 6 volts coming in. So this is 7K here and 1.4 volts or here. Well, 1.2 volts, I guess they'd say. So that would mean that they would have 8.8 volts, 7, and that I'm guessing that comes out to about 1.4. But what they're saying with this, when they have this switch here, is that when we switch it, it won't actually change this current, because this current is actually being set over here by this part of the circuit. Do that, and you see, we don't change that circuit or that current. Instead, across here, like no amps go through, obviously, because it's a short circuit. And right here, we have we just have between the VCE volts is just goes up higher. So there's more voltage being dropped across this transistor. Now you do have to be careful with this because there is a point where this will damage the transistor, like if that voltage drop gets too high. So that is something to watch for. But anyways, does anybody have any questions or comments? Like Holy Potato? I mean, Holy Potato just said that this sounds cool, but any other comments too, or you could just say that this is cool. I like that too. I'll just give a moment. Or even if any of you wanted to look at particular circuits too, I could pull them up. I did think in the description you'll find like my schedule of circuits that I'm planning to do. Keep in mind I've done the ones before this, so I've already done the Astable Multivibrator, the bandpass filter, and the high-pass filter. Did the bandpass, the high-pass filter before I switched to this stream because I mistakenly marked my stream as made for kids, which it isn't. Or I don't usually mark that down because, well, I want to. It's made for everybody, I guess. I don't know. But anyways, let's move on then to differential amplifiers. We'll do that. That's also the transistors. Did anybody a differential input? Ah, frick. Did it again. But Anyways, so this is what they have listed down as differential amplifier. Now this here is the output. This is quite a simple one, actually. I like this. The voltmeter. So a differential amplifier, as in the name, amplifies the difference between two inputs. So whatever is here and different from this, then this will output it. So what they are doing here, it looks like, or what they are wanting to show, is that they have this 40 hertz and this 40 hertz. And well, that is going to be rejected. And this 200 hertz one should pop out. So we should find some 200 hertz signal coming through this output here. Just wondering if I should try to explain how that works, or else, or if I'll just muddy the waters too much. Yeah, let's just go forward. So you see, we're getting that. Let me see the horizontal scale. Okay. So it says, here, we'll stop it. It says that this is 5 milliseconds per division. So we go from this point to this point, 5 milliseconds. That's what, like half a thing, roughly? So about 10 milliseconds, we do a full sort of tour through. So that would mean 10 milliseconds. It's 01001. So we don't. I would say we would only be getting 100 hertz, but obviously, I think it would be more. Go edit. So that's 100 millivolts. Yeah. This. So I'm just trying to figure out where all their checks are. Hmm. See, this is why I'm thinking I should actually go back and build some more circuits on the breadboard with op amps and transistors, because they are just a puzzling group of components sometimes. This is a classic circuit that really by this time I should actually really know well. So at this, obviously, we'd have 15 volts. Might circle back to this one later. Unless anybody in the comments has some ideas or wants to teach me some, has a nice link or something. I'm always open to hearing input. I would actually really love to hear some input. But if not, we are going to move on to sequential counters, and we're going to do a ripple counter one. Now these, here, sequential logic counters 4-bit ripple. Yeah. Yes. So, now this one, in the textbook I was reading, it said that I would never see a JK flip-flop. So it lied to me. I saw it on a simulator. Not that that really means much. Anyways, this flip-flop so when that's square wave again, 200 hertz. Let's just slow this down some. So when this clocks one time, it will flip this to 1. And then if this clock, then if that clocks again, flip that. Flip this one back to 0, which will flip this. And so on and so forth. And we'll just run down the line. There. So you see what's happening. This is just clocking. Then it goes 1. Then it clocks this again, which flips this one. That to 1 up here. And it just runs all over down the line. So, I think that is pretty cool. Since this is the last circuit I had on my list, but I'm not quite finished my beer from Blackbridge Brewery in Swift Current. I like this one. I am going to do, I think, some more logic circuits. Probably just discrete ones here. Does anybody have any comments or suggestions? No? Let's actually, I have one idea. I want to go look. I want to block inductive kickback right now. Just feel like it. So let's do that. So this will happen. What inductive kickback is, what I'm sure is they're going to talk about here somehow. I'll just have to work out how this circuit does that, is an inductor is all charged up, and then all of a sudden you switch. It's you tell it, oh, you can't actually do the current that way. It sort of freaks out and it tries to launch the voltage way up to force the current through, because it really, really wants the current to stay the same. And that is what inductive kickback is. It's just that rapid increase in voltage due to the reaction that, well, here, actually, let's look at that one first. It's the inductive kickback one. So let's run that. You see this is going, it's basically, it's right up there, and it has that current going through. We have no voltage now on it, but it will. Oh, hello. I'll just respond in the comment here. But yes, now we're down to a picovolt. But if I flip this on, all of a sudden this current is going to rush in to this circuit. The name of this circuit is, I think they just called it inductive kickback. So, like I was saying, it's like right now we have this current running really fast. The inductor is going to resist any change in current, which will happen if I flip this switch, because that then all of that current will, the current will slow down, because all of a sudden we'll start trying to charge this capacitor. So let's just do that. You see, now it went way up. Did you see? Here, let's slow down the simulation speed. So, well, we'll increase it here until we get back, because I don't know if you caught that, how much it just basically exploded right up. I've actually done it right on my breadboard, and I was like, so I wasn't thinking initially about it when I first did it, and I used the Analog Discovery 3, which is only can do plus or minus 25 volts. So I was sort of concerned that I could have heard it, but I don't think I did. So now that inductor's all charged up again, let's slow down this simulation. Really slow here. And now we'll turn this on. You see this inductor now max 2.2 kilovolts. So it just basically freaked right out, because it's like, hey, wait, you're trying to change my current, and I really dislike that. So now we're going back and forth, like you see here. The max still there is only 5 volts, and it's just along this inductor that we see these kilovolts. Yeah, but now we shall go back to that previous circuit where it was blocking inductive kickback. Does anybody have any questions? Comments? Concerns? No? Okay. If you don't know why I'm waiting sometimes, what I'm actually doing is I ask if there's any questions or comments, concerns, and then I put my beer down and I actually wait till I see on the um, on the screen that I've actually drank one of my beers. Um, the reason I do that is then I know whether or not you've seen it. So, this circuit, I think I see what they're getting at here. We won't see that kickback as much because we give the uh, the inductor a way to still like sort of satisfy itself. So we're going to charge this capacitor up to 5 volts. Then, when we opened this switch, in the case before this, say this was fully going around, this will be fully charged here. Going that way. And this will allow, then, when this current starts getting blocked here by this capacitor, this will actually let me think here. So actually the current will start flowing this way around. And it will block that massive like kilovolt amount of voltage we saw on the last one. So let's just run this. We'll get this charged right up. Now that is all charged. Let's slow down the speed again. And open the circuit. Now, yeah, you see what happened is we just saw this sort of release its tension through that that filter up top there. So instead of getting kilovolts, we got about, what was that? 8 volts. Which still is more, but it's more like, that's why, like, so going back to the textbook I was reading, Learning the Art of Electronics, it's actually called, the way that they dealt with it was they just put a diode that like it would go into conductive mode when that inductor started to blow itself up, which both are fairly valid. I could go look at that circuit and maybe do it another time. Actually, if I'm remembering correctly, I think I did do a video on it a while ago, though. Not sure. Yeah. So does anybody have any other questions, comments? No? Does anybody, just out of curiosity, how many people on this stream, anybody watching it actually like electronics or do a lot of it, or is like an electrical engineer or a student, or like just curious of it. And oh, here. There. We can go to circuits. And then I'll show you the one. There. This is the one that they had me do in learning the art of electronics. So let's just run it. We'll get that inductor all charged up again. Yeah, like I'm really curious. Just I know I've made this video vertical just because then I've noticed that when you make a video vertical, then YouTube starts putting it in the shorts feed, which then obviously gets more people. It gets shown to more people, which like I do that for a couple reasons. One, I actually do think that this vertical format looks good. You get a good view of me talking, and you also get quite a good view of the Falstad simulator at the top. But other than that, I'm really curious, especially for those of you who stick around for a fair bit, if it's just out of interest in electronics or if I just am like, I don't know, a bit of a curiosity and funny to watch or what it is. But anyways, I think I've talked enough. This inductor is obviously fully charged now. It's charged. Now let's see. I'll slow down the simulation speed again, just so we can watch it more. And what will happen, what I think will happen when I flick this switch around, is that you will see the voltage across this ramp way up again, and it will end up conducting this way to supply its own current again. Let's see if that happens. And yep, so this conducts itself through there. We get a 0.7 volt drop right there, and this basically automatically charged up. So, yeah. Does anybody have any questions or comments of, inductive kickback, and how you can deal with it? Blocking it either, like the first time I showed there was a capacitor and resistor. This time's a diode. For some reason I thought they only put the capacitor and resistor one there, but they did that mostly because then the capacitor resistor one is a passive circuit. I don't know if I I do. I guess I can't not agree with it. It's like a capacitive. It's just how they define a passive circuit, I guess. But like a diode, it's not. It's defined as an active component, but I don't know what I'm trying to say. It's still sort of a dumb component in my mind. It just does what it is designed to do. Like it doesn't. You can't program it or something. Yeah. It's just how they've defined it. Now I'm just looking at some weird circuits. I don't even know if I want to try and explain this one. Does anybody else want to try and explain it? Anybody know? What they call that here is flat ADC. No. Where did I find this? Yeah, let's do that. Tunnel diode. Now I'm just because I've went through all the circuits I've wanted to go through. So if anybody has some ideas for other circuits to go through, that'd be good. But let's just watch this tunnel diode. I always forget what it is supposed to do. So we got this triangle wave generator, and then this is the voltage across the tunnel diode. See if there's some other ones here. We are going to stick with tunnel diodes, though. You know what we could do? I could sort of break from normality. It's Google tunnel diode. Ooh. Semiconductor that exhibits negative resistance. Huh. That's odd. Let's just think about this some more. Okay, here, I'm going to slow this speed down. See, by negative resistance, yeah, so its amperage is increasing while its voltage is decreasing. Wow. Now, like as you can see, I'm obviously I went like for just for so you know, I took when I was at university, I was a physics student, and I took a few courses in electrical engineering, but it's only recently that I've really dove deep into circuit design and electrical engineering type things. So I am sometimes just not aware or knowledgeable of certain components. This is one of them, and it just disrupts my thinking, which is why I might seem a bit uh, unsettled by it. Because now, while most things, or some things, don't obey Ohm's law, um, this like this tunnel diode just completely does the opposite of Ohm's law, which um, I find personally a bit disturbing. Um, does anybody know? Does anybody have any know of any good applications for a tunnel diode? It's such an odd thing. Sure, I'm just not being creative enough. Let's look at what else they have here for tunnel diodes. Relaxation oscillator. I guess you can do that with it. Anyways, I think my beer's basically done. I'm probably going to pour myself another one, but I am going to go to the hot tub for it. So that means I'm going to call this uh, stream here. I hope that people have gained something from it. I think I have again. This is again like some people might wonder why I'm sitting here, why I'm doing this. Um, it is primarily basically everything on my channel. Just to give some context, is stuff I am trying to learn. There is some channel goals, of course, like with these live streams. I do like how it ups the watch hours and such. But it is primarily I am trying to increase my skills in whatever I'm trying to increase it in. So like I know for a fact I've looked at my analytics and the videos. If I really wanted to get my channel healthier and better, would be to do the ones KiCad tutorials or ones like it, where I do short little videos just doing shortcuts and stuff, because those are the best, most successful ones I've done. But I'm trying to focus on learning electronics. That, while KiCad is quite important to that, doing the one that I doing that, those short videos on how to use KiCad isn't that beneficial to it. But with these videos, I'm trying to just like these live streams, I'm trying to improve my ability to communicate circuits to other people with a focus on words. And the reason for that is that then I can sort of present my circuits in a more understandable way. But anyways, I think I am going to stop it here. Thank you all for watching, and I hope you tune in some of my future streams, and please watch my most recent video. I really liked making it, and I put in a little bit extra effort, and I actually scripted some of it too. So yeah, but thank you and have a good